Okay, so an example here. We have a sample here of radium-226. In my last lecture, I talked about 228. I meant to say 226. That's the one I was talking to, and I talked about the radium isotope with a half-life of 1,600 years. That was radium-226, not 228. So what happens is radium-226, which has 88 protons in it, goes by alpha decay to radon, not radium, radon, Rn. Oops. Radon-222. That's got 86 protons. Any nucleus with 86 protons in it is radon. Plus the alpha particle, which you'll remember is really helium-4. 2 protons, 2 neutrons stuck together nice and tight. That's the alpha particle. So what happens here is the sample produces alphas. Okay? And we start off with 3 times 10 to the 16th of them. We've got 2 questions here. Oh wait, I didn't write the half-life. Half-life is 1,600 years. Boy, this is a very squeaky pen. Which is equal to 5.05 1,600 years is 5.05 times 10 to the 11th, is it? Where'd it go? 10 to the 10th seconds. All right. We have to be careful when we talk about activities, talk about radioactive rates or activities. We have to keep things in seconds because the Curie and the Becquerel, those units are both expressed in terms of seconds. So, seconds, converted our years to seconds here. And so the question that we're asking is, what's the initial, first question, A, initial activity or not? So when we first start the clock here, we have that many radium-226 nuclei. How many alpha particles are going to be produced per second? That is the initial activity or not. And second question we're going to answer, question B, is how many radium-226 nuclei are left I think this will fit. Yes, after 5,200 years. Is that visible? Yes. First question, what's the initial activity or not? And the second question is how many are left, if we start off with this many today, how many are left after 5,200 years? Okay. And so that question is really asking to calculate N, capital N, after 5,200 years. So let's do the maths here. Part A. Remember the formula I wrote up last time, that R equals lambda times N, right? That's true for at any time during the decay. Okay. Remember the number of these radon-226 nuclei is going to follow that. I'm not going to draw it. I don't have room to draw it here, but it's going to follow that exponential decay. And this is true at any time during that decay, including the initial time. So we can write it that way. All right, we want R naught. We want the rate, the activity at the beginning when we start the sample off today. And we can find that this way. Well, we know N naught, that's given to us. All we need to do is find lambda. And lambda is natural log of 2 over the half-life, okay, which is 0.693 over the half-life. We're given the half-life here. That was a given in the problem. And so we get lambda is 0.693 divided by this big number here, 5.05 times 10 to the 10th seconds. So lambda is equal to 1.37 times 10 to the negative, is it 11th? Yes. Inverse seconds. That's lambda. Okay, we were given half-life, so it was easy to calculate lambda from it. All right? And so we can find now R naught is this number times 3 times 10 to the 16th. And you do that, and you get 4.12 times 10 to the 5th decays per second. So it's about 412,000 per second. Every second that ticks by, when we start our sample off, you get 412,000 of these reactions every second. Okay. Even with a half-life of 1,600 years, these things start off immediately. So you're going to get 400,000 of these decays per second. If you convert that into Curies, you'll get R naught is 11 microcuries. Micro 10 to the negative 6. Basically, you just divide that number by 3.7 times 10 to the 10th, and you get 11 microcuries. All right, that's the definition of a curie, and that's why we needed to keep seconds. Convert our half-life into seconds here. Okay, that's the first answer. That's the answer to A. That is our R naught. So that is done. And now we want to know how many radon 226s are left after 5,200 years of this. Okay, well, 5,200 years, so this is B. I'll start down here, then I'll move up there. 5,200 years. The easiest way to do this is to convert this into half-lives. So 5,200 years times, is this going to fit? Yes, it's going to fit. 1,600 years per half-life equals, it'll just fit, we get 3.25 half-lives. Okay, does that fit in there? I believe so. So 5,200 years, another way of expressing that, right? The question is how many of these radon 226s will still be around after 5,200 years? Well, 5,200 years is 3.25 half-lives. Given that, it's very easy to find how many we have left. Let me do a different color here. N is N naught, you remember this, times 1/2 to little n power, where this number here is N, 3.25. That's the number of half-lives. That's what N, little n means, the number of half-lives. So there are 3.25 half-lives in 5,200 years. So all we need to do is multiply our original value here, 3 times 10 to the 16th times 1/2 to the 3.25 power. The Y to the X button on your calculator will do this nicely. When you do that, you calculate it out, you get 3.2 times 10 to the 15th. That is the answer to B. 3.2 times 10 to the 15th particles are left after 5,200 years. You've really only cut down the number by not even, you're about 1/10 where you were where you started. So hundreds of thousands of these things going off per second. After 5,200 years, you still only worked your way through about 1/10 of them. So there's about 90% of these left. Okay. No, that's not right. You have 10% left. You've worked your way down through. You have, after 5,200 years, you have lost 90% of the original sample of radium-226. Okay. You've gone from 3 times 10 to the 16th down to 3 times 10 to the 15th. You've 1/10 of the value you started at. You've lost 90% of the original radium-226. You've gone from 3 times 10 to the 16th down to 3 times 10 to the 15th. That's your answer to B. The end.